I'm going to go on a little mini soapbox right now, just because I want you to hear me. In my opinion, I feel that you as a senior class should be able to choose PreCalculus over a personal finance course. I feel that a personal finance course would be a lot more useful to most students than PreCalculus, but I am not in charge of the world. So hear me now. Would you like to retire at the age of 35?
Yes, ma'am.
I would love to have retired at the age of 35 if I had listened to myself back when I was your age. Nobody actually told me this when I was back your age. I got married, had children early, and got stuck in that whole, living from paycheck to paycheck, which fortunately I don't do that now. But society today lives on debt. Okay? You should never, ever, ever be in debt. The one thing you might be in debt for is a mortgage. And when you get your mortgage should never be, your mortgage payment should never be more than 25% of your take-home pay. Not what you get paid, but your take-home pay. Never more than 25%. And then if you have zero debt, that shouldn't be an issue. And you should always pay off your mortgage in 15 years. So if you can't afford that 25% take-home in 15 years, then you bought too big of a house or too expensive of a house. So if you can handle living meagerly compared to your friends for several years, then eventually they'll still be working because they're working to pay for all their toys and living paycheck to paycheck while you're sitting doing whatever you want to at the age of 35. So you could conceivably rack up $1 million by the time you're 35, but starting now, and I mean today, you have to learn to live off of 50% of what you make, not what you take home, but what you make. That's before taxes. So if you put away in investments, and you do have to invest it correctly, so you want to have a good investment advisor. But if you learn to live off of 50% by the time you're 35, you ought to be able to have at least $1 million. If you want to have more than $1 million, then you just work a little bit longer. You think I'm crazy, but I'm not. I mean, just think about it. Now, granted, your friends are going to be going on trips and buying cars and buying toys and doing this and that. And meanwhile, you're living meagerly. Okay, but the end game here is at 35, I could choose if I wanted to retire and or just work part-time and tool around and do what you want to do. Now, you might not have enough money to tour the world at that rate because you want to live off the interest of your investment. You don't want to ever dip into your principal. And if you invested at 10%, your average investment rate was 10%, you had $1 million, could you live off of $100,000 a year if you have no debt? Sure you could. It's a lot of money when you don't have any debt. You could live quite comfortably. So as you work and you get paid more money and you get different jobs, you continue to live off of half of that income. As you get a spouse and they get a job and they contribute or whatever, maybe they don't. This could be where maybe your spouse is a stay-at-home parent. You're still living off of 50%. Then when you feel you've had enough money that you can retire a whole lot earlier than 65 years old. So a lot of you, your biggest thing right now is you're thinking about, if you haven't already, buying a car. It's your car to drive, right? So here's a concept. How about saving the money for your car before you actually buy the car? You guys have fallen into this concept of, I want a car, I want it now, and so I'm going to go get it on credit. Instead of waiting, saving the money, driving a piece of garbage car, saving your money, don't get pulled into that thing, well, it's more expensive to fix my car than it's just to buy a new one. That's not true. Do the cost-benefit analysis on it. So you just have to suck it up and save enough money until you buy a car that you like. And then once you have that car, you continue to save money for another car. Because you know that within 5 years or whatever, you might need to have a different car, or you might have to repair your car. So then you save money in a car fund for that. In addition to that, you should also be saving for an emergency fund. Thank you, dear. You should always have saved up 6 months worth of expenses in case you lose your job, in case you get sick, something like that. That way, when there's an emergency that occurs, you don't have to rely on credit. And it is a myth that you have to have good credit. Good credit score, so therefore I have to have credit. If you never get into debt, is there any reason to have a credit score? No. The only time you need a credit score is if you get a mortgage. After for that, I mean, I have no debt. I have no reason to go get credit. I have a good credit score, but I don't need a good credit score. Because when I go to buy a car, I'm not going to buy a car on credit. I'm going to buy it with cash. And when you buy things with cash, guess what you get to do? You get to actually deal with them. And say, I'm paying in cash, so what's the actual cash price? Usually it's less than the credit price. So, I mean, you need to think about these things now. If you're somebody who has to pay for your education, well, I thought about that when I was really young, because I knew my parents weren't going to pay for my education. So in school, I got really good grades because I knew I needed a scholarship. And so I didn't have to pay for my education, so I didn't have that hanging over my head. But there's a novel concept that you could actually work while going to school and pay for your tuition at the same time as going to school. You don't have to go to a fancy $100,000 a year school. You can actually shockingly get the same education over at Arizona State University, go Sun Devils, as you could at, I don't know, Stanford, I'm thinking is pretty expensive. Am I right? You could get the same education here at Horizon High School as you could at, let's pick a private school, Xavier. Xavier's very expensive. If you're a well-motivated student, you get as good a quality education, if not better, here at Horizon as you do at Xavier. It's a matter of your motivation. So think about that. I'm off my soapbox. Here we go. So you're going to become millionaires all at the age of 35, right? You're like, I don't know if I want to live like that. But then you're working forever, just to let you know. And some of you are thinking, I'm going to marry somebody rich. I thought that too. And I fell in love with somebody who wasn't rich, but very nice, very good man. So I had to work for a living. So, any thoughts on that? Well, it just depends. Yes, some. It just depends. It depends on how much money you have and what you intend on doing with it. But that's why I say you need to have a good investment advisor. Yeah. And, you know, and then that way, if you lose your job or the economy goes south and you have no debt, it doesn't affect you as much. If you lost your job and you had no debt, you would not be as nervous as somebody who lost their job and has oodles of debt. Am I right? Think about the stress in your life that I mean, I have a far less stressful life because I get paid a lot of money in the future, but I live quite well. Why? Because I don't have debt. I don't have debt, but I do drive a 1997 car, but it only has 49,000 miles on it. So it has very low miles. It's a very nice car. But I mean, you make choices. I don't have a fancy car. I don't have a $800 a month car payment. I just saw that Jaguar, $800 a month. I'm like, they seriously put that on TV? Who does that with a straight face? Okay, some of you are not thinking, I'm not thinking Jaguar, but I don't know. What car are you wanting? A brand new car, what would you want? Camaro? How about a Camaro? $40,000 to $60,000. 40 to 60, you could buy a house for that. It's not a very nice house, but you could buy a house for that. You could live in that car. Just saying. Just saying. Think about your future, because I know that you're like, you don't think past tomorrow, some of you, but think about your future. So let's talk about investments. I want you thinking about investments. So there's a difference between compounded interest and simple interest. So let's just start with interest that's compounded once a year versus what's called simple interest. With simple interest, you get paid, this is just interest. You do not get paid interest on your interest. You just get interest on principal only. So for instance, let's say I have, and we'll make it easy on myself, year 0. I have $100 that I'm putting in the bank at 10% interest. Good luck finding 10% interest at a bank on a savings account. It's more like less than 1%. But let's just assume I found a really great bank. After year 1, at the end of the first year, I would get 10% on $100, which is what? It's $10. So I would now have $110 in my bank. This is assuming I don't touch my investment. Then after year 2, I still get 10% on only the principal. So I still get another $10, so I get $120. And then at the end of year 3, which I'm going to stop here, I get $130. Now mind you, it's only a $100 investment. Consider that investment being $1,000, $10,000, $100,000, $1 million. Okay? So 10% on $1 million is what? $100,000 each year. That would be nice, right? So if you could have $100,000 in the bank, and you could have an average investment rate of all of your investments, because you would diversify it, of 10%, could you live off of $100,000 a year? Sure, if you had no debts. There's the key. You have no debt. So I'm just planting the seed. You're going to come back and give me a bonus for just making your life happier. Someday you'll find Mrs. Murray. All right, so let's assume the same thing, but with compounded interest. I get paid interest once a year with compounded interest here, on this example, but I get paid interest on my interest. And there's a lot of debt that is compounded interest. You pay interest on your interest as well, especially if you look at your credit card statement. If any of you have a credit card that you have, put money on it, and they'll say minimum payment. Oftentimes the minimum payment is less than the interest that they just tacked onto your bill. Are you ever going to pay that card off? No, you're not even paying the full interest amount, much less your principal. And so they've got you. If you just, I'll just make minimum payments, you're never paying that off, ever. Well, now they're required to put on there how many years it'll take you to pay off that amount. If you pay the minimum payment or $100 or whatever, they're now required to put that on the statement because people didn't realize that they weren't paying their debt off. So I want you to be smarter than the average person. So you're getting paid interest on the interest, so we still have a 10% rate. In year 0, we're still putting in $100. So at the end of year 1, I'm getting 10% on the $100. So at the end of year 1, I still get $110 just like simple interest. So far there's no difference after 1 year. However, what happens after year 2? After year 2, I'm getting paid 10% on the $110. So what's 10% of $110? $11. So I'm going to add $11 to my 110. Now I have $121 at the end of year 2. That's a $1 difference, whoop whoop, between the two. Now mind you, we're just looking at a $100 investment. Now if we change that to $1 million investment, now we're talking some good change, right? So the more your investment, the more difference this would make. After year 3, I'm getting paid 10% on $121. So what's 10% of 121? $12.10. So I'm going to add $12.10. So I now have $133.10. Now $3.10 more. This is an exponential difference. Do you remember the graph of exponential goes like this, and then poof, it all of a sudden starts screaming up quite quickly? It starts out slowly at first, and then boom, the exponential difference is huge. So the longer you hold your investment when it's compounded, the more money you make towards the end of that investment. With simple interest, this is linear. You're making the same amount every year. It's the same change, so it's a linear change. So it's going to take you a lot longer to get to the same money than it does with compounded interest. So my point is, compounded interest is better. If you can get compounded interest, you want it. Now, the reverse is also true. If you're paying interest on something, I prefer to pay simple interest. So I'm going to pay less than compounded interest. So it does work both ways. It just depends on your perspective. So let's look at an example. Interest compounded annually versus the simple annual interest. So suppose George Jones, George is my buddy, he invests $10,000 at 6% annual simple interest. So he has chosen annual simple interest. He didn't go shopping very well. But Miss Mary quite contrary. She was a little contrary, so she went and found a different investment. Same amount of money, $10,000, same interest rate, but hers is compound interest. So she's getting interest on her interest. So the question is, compare the values of both investments after 10 years. So I'm going to give you the formulas. You just have to know how to use them. So within these formulas, what do you think the P means? Your original principal. The R is what? your interest rate. And the n would be what? This is your number of years. So that n there, they don't use t, I don't know why, but this is your number of years that you hold your investment. And so same thing here, you got your rate, your number of years, your initial. It's just, they look different. This is linear, it's not raised to an exponent, whereas that's exponential. So here we go, we're just going to plug in the formulas. I multiplied this by 10%, really 1.10. So if I took my handy dandy calculator and I just took my investments of $100 and I multiplied it, if I multiply it by 10%, I have to add it back in. So if I multiply it by 1.10, it's going to add it back in automatically. So after year one, get the glare off of there. After year one, I have $110. Then I multiply that by 1.10, 100% plus my 10%, now I got my 1.1 times 1.10. So I just keep multiplying by 1.10 each and every time. And it just continues to grow and grow and grow. So it's the same multiplication. And what this does is it allows us, so I don't have to do that 10 times. So we come up with a formula that will enable us to just plug in the years that I want to hold it, and it'll tell me what my amount is that I want. And then we're going to compound different time periods other than a year. So for George, so let's look at George. So we're going to use our formula A, and I'm going to plug into that formula $10,000 for his initial investment times, he's using the simple interest though, so we want to be using this formula over here. So times 1 plus my rate, I'm going to use 6% as a rate, 0.06. So my rate is 0.06 times the number of years I'm holding it, and I'm holding it for 10 years. That's it. So we're going to throw that into our calculator. Be careful when you plug it in. Nice use of parentheses. So 1 plus 0.06 times 10. You get $16,000. See, now we're talking about a bigger chunk of money than $100. We're talking about $10,000. And if you think about it, what is 10%, or I'm sorry, 6% of $10,000 times 6%? He's getting $600 a year for 10 years. What's 600 times 10? $6,000 added to that 10,000. That's where that came up with. So he got a nice chunk of $16,000. Now let's look at Mary, Mary, quite contrary. Let's look at her value. So Miss Mary. So we're going to put in the same values, $10,000, but we're using a different formula. We're using the compounded formula. So we're using this one here, times 1 plus. My rate is still 0.06, but this time, instead of multiplying that by 10, we're raising this to 10 years, because it's an exponential function. So then in here, be careful, again, how you put it in. You should expect her to make more money with compounding interest because Arnold, you're taking notes, dear. It's not a choice. So you should expect with compounding that you should make more money, and indeed she does. And she makes $17,908 and how many cents? 48 cents. We're going to always round to dollars and cents when we deal with money. And by the way, I'm not sure where you learned this, but the dollar sign goes in front of the money, not at the end. That would be in Europe. Did y'all put it at the end? Arnold? Yep. So in the U.S., you put your dollar sign at the front. We like to be different. Don't ask me why. But there we are. I don't know how you all got through school and put the dollar sign at the end. I can understand it if you're from a different country than the U.S., but the people who are doing it are from the U.S. So which investment would you prefer? I definitely want Mary. She almost got $2,000 more than George. So being contrary was to her advantage. All right, so let's look at different types of compounding. So compounding is better. There are different types of compounding. There's plain compounding and compounding continuously. You can find compounded continuous interest out there, and that's the best compounding of all, but good luck finding it at a decent rate. Like you could find compounded continuous interest at a savings account at less than 1% of interest. It doesn't really do you a whole lot of good. And what compounded continuously means is it's compounded continuously. There is no stopping period. It's continually compounding. Whereas compounded interest has different periods of compounding within the year. So you can have annual, which is what we just looked at. So annually would be one time during that year. Then next would be semi-annual. So girls, a semi-annual sale means it happens how many times a year? Twice. So semi-annual means that it compounds. There's 2 compounding periods during that year. Then we get to quarterly. Quarterly means what? So there are 4 compounding periods. Then we would get to monthly, which is what? 12. Then weekly, which is, here's where you start to break apart. No, it's not 56. It's 52. Although that's a very popular thought, 56. It's 52 weeks in a year. Well, when you start getting paid like a salary, you start to figure out you have 52 you have 52 divided by 2 pay periods, or some of you get paid per week. You get 52 paychecks a year because money starts to become important. All right, so then you have daily. What would be your daily compounding? 365. Now I know that there's technically not 365 days in a year. It's like 364.25, but we're going to go with 365. Make life easier. This is all related to K. K in this formula, K is the number of times compounded in 1 year. So that's your K, and then they've converted the time back to T. So that time right there is number of years held. Number of years that you hold that investment. So K appears twice in the compounded interest formula, both in the exponents and in the denominator underneath the rate. So questions about compounding before we actually run some compounded interest problems. Okay. So let's look at poor Robert. Poor Robert's having, actually Robert's thinking about his investment. So he only has $500, which isn't a lot, but it's better than 100. So he's investing $500 at 8% annual interest compounded monthly. So compounded monthly is how many periods? So K is equal to 12. That's what that's telling you. And plus you're using the compound interest formula. Now there's a difference between the compound annual interest formula and the compound interest for any compounding period. So please note the difference. You could still use this for annual interest. It ends up being this though. Switch now. The 8% is our rates. So what are we going to use for our rates? 0.08. And then what's the 500? That's your P. So let's make our equation. So we've got A for his amount earned equals 500 times 1 plus your rate is 0.08 divided by your 12, that's your K, raised to the 12, that's your K, times, we want to know the value of this investment after 5 years, isn't that T? So that's why I'm putting 5 years in here. Is that fuzzy or clear? It is fuzzy, right? Thank you for being honest. I don't think it's going to get clear unless I move it in. And then if I move it in, I can't see my calculator, so we'll have to deal with it. All right, so we're going to throw that in our calculator. Be really careful, especially if you have the older calculators. You want to make sure you put that in parentheses, whatever your exponent is. And in fact, I would even go so far as to multiply 12 times 5, which is what? 60. So if I were you, I'd be putting 60 in there rather than the 12 times 5. So 500 times 1 plus, get in the habit of putting that in parentheses, especially if you have an older calculator, 0.08 divided by 12, and the interior parentheses and the outside parentheses, and raise that to the 60. And so what that means is we have a total of 60 compounding periods in that 5 years. So you're going to have 60 times of getting interest on the interest. Here we go. Survey says $744.92. So after 5 years, he will have made a little bit of money. Not a whole lot, but a little bit, because his original investment was not much. If you don't risk a lot, you don't make a lot. Of course, I'm not advising you to risk a lot of money either. That's all a matter of your choice. I'm talking to your investment advisor.
So he's paid $244?
Yes, he has. $244.92 over that 5 years that he didn't have before, which is nice. All right, so part B, how long will it take for his investment to grow to $3,000? So where is that $3,000 going to be placed in the formula? Our P is still 500, so it does have to be A. So our original investment hasn't changed. We want to know when will that $500 grow to $3,000? So remember, this is exponential, so it didn't, it took 5 years just to grow to $700 and almost $50. How long did it take to go to 3,000? Well, exponentially, he starts getting more and more money every year as he holds that investment. The longer your investment, the better off you are. So here we go. We're going to put the 3,000 in for A, and I'm going to use this formula right here, but instead of the 5, that's the part that we're going to replace with a T because we don't know how long. So we still have the 500. We have the 1 plus 0.08 divided by 12 because it's still compounded monthly, but we raise it to the 12t. Now, you did learn in section 3.2 that you can put this into y sub 1 and this into y sub 2 and find their intersection. But we also learned yesterday how to use our math and not do that, correct? So let's get the base by itself. This whole thing being raised to the exponent, this whole thing, including the exponent, that's my base. What do I want to get rid of? The 500. So don't I divide it? Because it's being multiplied. So the 500s cancel, so do the zeros. So I'm left with, I'm going to go in this direction, I'm left with 30 divided by 5, which is 6. If you don't mind, I'm going to put the power on the left. So I'm going to put the 1 plus 0.08 divided by 12 raised to the 12t. I'm going to put that on the left. And I'm going to put 30 divided by 5, which is 6, on the right. Now this is a bit of a mind-blowing kind of thing, a little bit, because you're not going to like the number. But let's just pretend like my base is, 15. Okay, 15 to the 12t equals 6. How are you going to solve and get that t out of the exponent? So ignore the ugly number in there. How are you going to get, how did I teach you to get that out of there? Take the log of this base of both sides. So that base is a little ugly. So let's find the actual nice little number. Well, it's not exactly a nice number. But let's see what this base actually is here. So let's take 1 plus, and in parentheses, 0.08 divided by 12. See what that is. It is a repeating decimal. So on paper, I want to use that entire decimal when I take the log, but I don't want to write the whole thing down. You can't because it repeats. So we're going to just abbreviate it, but in our calculator, we'll still use this entire thing here when we take the log. But on paper, we're going to write down something different. So on paper, I actually have 1.006 repeating raised to the 12t equals 6. Everybody agree that that's the same? Just making it look prettier. So we're going to take the log of both sides, and it's a plain log because there's no e involved, so it's not a natural log. And I want to take the same base as the base of my exponent, or my power. And so I'm going to take the log of base 1.006 repeating of both sides. The log of base 1.006 repeating of both sides. Now these bases are not the same. I know they both have a 6 in them, but they're not the same. However, these bases are the same. So because these bases are the same, and I'm running out of room, I'm going to, the whole left side becomes what value? And those bases are the same. Just 12t. Equals, and the right side becomes the log base 1.006 repeating of 6. Now how do you solve for t? Ignore all that. Just divide by 12, right? So divide by 12, divide all of that by 12. And so t is approximately equal to, now watch what we're going to put in for that base of 1.006 repeating. So we have to take the log of 6 first, right? So log of 6 first, divide that by the log of that base. Well, I want to use a proper number. So the log of that proper number, wasn't it this over here? 1 plus 0.08 divided by 12. I want to take the log of the proper number. That's just my change in base, right? Then I want to divide that by 12. What'd I get? And since we forgot what we're solving for, what's t? What's t, unit of measure? It's years, isn't it? And so we could actually check our answer to see if it's correct if we put this formula in right here, just that part of the formula, right there. Put that part of the formula in your y equals, and you go to second graph and look at your table, and you can put in 22 years and put in 23 years and see if your investment became $3,000 somewhere in between, and you would see that change. Questions on that? It's so silent. It's Friday, I can tell. Even Ben's not chipper. All right, next question. What interest rate would be needed to double his investment in 4 years? You're going to love the answer to this one. So he's like, okay, I want to double my investment in 4 years because he has plans for his money in 4 years. So I need to figure out what interest rate I need to shop for. So here we go. He wants to double his investment. What is that going to be? So it'll be $1,000, and where's that going to go in the formula? That's going to go in A because that's the result that he wants. We still have now 4 years as our T, right? So that's our T. And we still have our original investment of $500 and our interest rate and our compounding. So that's all the same. So we're going to put the $1,000 in A equals 500 times 1 plus 0.08 divided by 12 raised to the 12. But we're going to multiply this time by 4 years. Wait a minute. How long? Oh, yeah. Oh, I don't know right, right? That's why. I knew. I'm like, where's my variable? So that's gone. That's what we're looking for. So make that your R. Right? Well, that's our unknown. Well, that looks like fun. Okay, R is imprisoned inside the parentheses that is raised to the exponent, so it's the base of the power. Well, in order to do that, I want to get this power by itself, so get rid of your 500. Divide by 500. What do you get? You don't get 500, what do you get?
2.
Yep, you get 2. So 2 is equal to 1 plus R over 12 raised 12 times 4 is 48. Now let's ponder this. Let's just say that you had just r in here. R is raised to the second power. R squared equals 2. How would you solve it? You take the square root of both sides. But r is raised to the 48th power. What do? Take the 48th root of both sides. But it's not r that's raised to it, it's that whole thing. So you still take the 48th root of both sides. So 48th root, don't panic, and the 48th root of all that. So what that encompasses for us is that the exponents and that root goes away, and all I have left underneath here is that 1 plus r over 12. So if you will indulge me, I'm going to put the 1 plus r over 12 on the left. Equals, and then the 48th root of 2 on the right. Now I'm solving for r. What do I have to do? Subtract 1. So I subtract 1, subtract 1, and then I'm running out of room, so I'm going up here. So I have r over 12 equals the 48th root of 2 minus the 1. Now how do you solve for r? Multiply by 12 and multiply by 12. So r is actually equal to 12 times the 48th root of 2 minus 1. So how do we do that on our calculator? Where do I find the nth root button? Where is it located? In the math button, math menu. So I'm going to put my 12 in first, but the majority of your calculators are going to require you to put the root in first before you hit the nth root button. So I'm going to type in 48. I'm going to go to my math button, and I'm going to look for or scroll down to the x roots, or you could just type in 5. My calculator automatically puts it in there. The older kind of brick calculators, it just puts it in front with a little x, raised x. It took it to the 48th root. And then you want to make sure you put 2 in here, right click out of there, and then your minus 1. The older calculators, you don't need any parentheses or anything like that, but you do need to end the parentheses here so that you've got the 12 times that whole amount. And then just double check and make sure that you got the same answer as I did. If you didn't, we did something wrong. Yes?
For the 48th root, why is it plus or minus?
Why is it not? Because I'm not going to have a negative interest rate, but that's a good question. I know my interest rate is going to be positive, and that's why. It is an even root, so she has a good point. Do 12 times and then 48, hit your math button, and go to the 5th one, and it automatically set there for you. Okay, thank you. Anybody else have trouble with that? Okay, so if you don't get this, then we probably put it in wrong. So r is approximately equal to, and that's a decimal equivalency, 1745. I want to write it as a percent. So what is that approximately equal to? 17.45%. Good luck finding that interest rate. That would have to be a fairly risky investment, would be my guess, especially if you're only investing $500. The higher your interest rate tends to be the riskier of your investment, tends, emphasis on tends. It also depends on what you're investing in. So as I said, I highly suggest you talk to an investment advisor, because I certainly am not one. It's not my specialty. I just happen to know some things about investing. But I do rely on my investment advisor. Wells Fargo. I like Wells Fargo Bank. They're very nice. They have popcorn. They say hello when you walk in. No, they can't be bad if they give you popcorn, right? All right, so let's look at compounded continuously using this formula here. What that means is I can't count the number of periods of compounding within that year. It's just innumerable. It's constantly compounding. You'd think you'd be making a lot of money, but it just depends on your interest rate. You definitely make more money than you would at any other type of compounding. But I just asked one of my students' fathers, has he seen continuous compounding? Because I don't ever usually see it, but he said he sees it at Wells Fargo in savings accounts. But the interest rate is like 0.1%. Is that a very high interest rate? No. So even though we're continuously compounding, we're not making much money at 1/10 or even 0.2% of interest is not much. So suppose poor Robert again has his $500 investment, but it's now at 8%. It's still, well, that's still the same percent. So we're now looking at this in continuous compounded interest versus he was compounding it monthly. So let's see what he makes. So using this formula, we've got A equals, his original investment was $500 times E to the R, our rate is still, 0.08 times T. So we're going to put T in here because they want us to find the amount of his investment after 1, 2, and all the way to 7 years. So you can use your calculator for that. So we're going to put this into the y equals of our calculator, and we are going to use x instead of t. So go into your y equals. Oh, look at that. I happen to have it in there. Imagine that. So put your 500 e to the 0.08 and then x. Now, if you go to seconds graph and try to look at your table and try to input values in there and won't let you input values, you want to go to table set. And so you want to go to second, table set, and you want to make sure that your independent variable is allowing you to determine what you want to put in there. So if it won't let you input values, you've got to know to go to your table set, scroll down, highlight ask, and hit enter. Then go to second, graph, and it auto allow you to put in those values. So we want to put in the values all the way through 7. And you're just going to record those in a table as your answer. So I'm going to make my table of values of T for time and A for amount. And so all this does is allow us to be able to compare what we just wrote here. So at $500, at 4 years, what was our 4 years? At 4 years, he made $744.92. Right? Oh, was that 5 years? Sorry, 5 years. I say, how is it less? Okay, so at 5 years, this was $744, but at 5 years with continuous compounding, we make more. So the best compounding is, and again, we only have $500 invested, so it does like, less than $1 more, or whatever it is. Imagine if it were a million. Now we're talking about some difference. Plus, this is the early part of investments. Remember exponential, the graph starts out slow, but then it really skyrockets towards the end. So the longer I hold my investment, the more money I make at the end, and it just gets bigger and bigger and bigger. And if I don't touch that investment, it starts to make a nice little nest egg. So question is, how long will it take Robert to double his investment this time? The last time it took 22, no, that was for 3,000, so that was a lot more. So we didn't figure it out on the previous side, but this time we're just going to double. So what's double his investment? Oh yeah, we did. We wanted to know if it, we wanted to know if he could double his investment in 4 years. So let's see what happens on this one. A double investment to $1,000. That's going to go in for A. And so we put in $1,000 in for A equals, our original principal was $500, e to the 0.08 t. So we can use our math. I want to get that, this will be a lot nicer than the last one. I want to get that power by itself. What do you do first? Divide by 500. And so I get 2 equals e to the 0.08t. How do I get t out of there? Natural log, because we have e involved, right? So I'm going to take the natural log, because it has a base of e, of both sides. And the whole purpose was so that those bases became equal, so that that right side, and if you will, again indulge me, I'm going to put the right side on the left, so it becomes 0.08t equals the natural log of 2. How do you solve for t? Divide by 0.08. So that's a lot nicer math than the last one that we did. So t is approximately equal to, throw that into our calculator. I would find the natural log of 2 first, and then divide that by 0.08. So in 8.66 years, he will have doubled his investment. We could have put a $3,000 in there to kind of compare it to how many years it would take to get to $3,000 with what we did on the front with the compounded monthly interest. But this is just something a little different. Now, my favorite piece of this entire lesson is this annual percentage yield part here. If you do ever purchase a home or a car under a loan, which of course I don't recommend you buying a car on a loan, they will make you sign a piece of paper that lets you know exactly what interest rate you're really paying. For instance, the first house I ever bought was at 10% interest. That was the economy at the time. That was many, many moons ago. Now my interest rate on my loan is 3%. But when you go to sign that mortgage, you have to sign a piece of paper where they have to tell you that really I'm paying more than 3%. Because if you wait the entire life of the loan, 30 years, to pay it off, you're paying interest on interest as well. And so you actually end up paying more than what it really is. And the more principal you get paid down, the less interest you end up paying, and so it starts to reverse itself. But we're going to use this formula to compare, and we're going to be on the happy side of things and assume that we are investing money and we're comparing our investment rates. So Amber invests $3,000 with Wells Fargo Bank, and it really doesn't matter for our purposes how much you are investing. It's the percentage rate and the amount of times it compounds. So she's investing 5.2% with annual interest compounded quarterly. So compounded quarterly is compounded is K, quarterly is how many times? 4. Her 5.25% is her rate, and what are we going to use for that? 0.0525. You want the whole thing, don't round. That's all we need. We need just a rate and the compounding, because those are the only variables in that formula up there. So our APR, we don't care about the 3,000, our APY, is equal to 1 plus, and then our rate, which is 0.0525, divided by our compounded quarterly, which is 4, all raised to the compounded quarterly again, which is 4, and then you minus 1. Be really careful when you put this in your calculator. There's a lot of room for mess-ups. Now you should come up with a rate that's fairly close to the 5.25%. So if you're really off, you probably did something wrong. So we have parentheses, 1 plus, and if I were you, I would put this in another parentheses. Just saying. Especially if you have an older calculator. So if you use double parentheses, you have to have double parentheses at the end. And then raise that to the 4th power. Right cursor out of your exponent, and then do minus 1. And that's my decimal equivalency. So my APY is approximately equal to 0.0535. So my APY, my annual percentage yield, is approximately equal to what percent? 5.35%. So I'm actually earning more interest than what they're saying because it's compounded interest. I'm getting interest on my interest. So it's nice to know that, oh, I'm really making more. So why is this valuable? If I have to decide between two different investments, so here we're going to decide between two different investments, it's not always the investment that yields the highest interest rate. It depends on your compounding, it depends on how long you hold the investment. In general, the longer you hold the investment, the better the higher percent yield is, and then the shorter you hold the investment, the better the shorter yield is. It just depends on the compounding. It totally depends on compounding. So look at this one here. Which investment is more attractive? One that pays 8.75% but it's compounded quarterly versus one that is 8.7% only but it's compounded monthly. So this one has more compounding periods than this one, but it's at a slightly lower interest rate. So let's find our APY. And just so I can tell the difference between the two, I'm going to put this one as a sub 8.75%, just so that I can tell the difference. It has no mathematical value here at all. Equals. So apply your formula. 1 plus my rate at 8.75 is 0.0875. Compounded quarterly means that K is what? 4. So we put a 4 under here. Raised to the 4, so that K again, and minus 1. We'll calculate that in a minute. So let's set up the other one. So our APY for the 8.7% is equal to 1 plus, my rate is 0.087 only, but my compounded is monthly, which means that this time my K is what? Monthly. 12. So I'm going to put a 12 down here, and I'm going to raise that to that K of 12, and then minus 1. So now let's calculate each of those separately. So the first one, so we get 0.0904. So that APY is about 9.04%, which is higher than the 8.75, which is nice. Versus, I'm going to do the other one. That one I get 0.906. Approximately 0.0906. And that's for my 8.7. So which investment is more attractive? I realize it's not by much. But over time, if I held my investment for a longer period of time, which one would I want to choose? The 8.75 or the 8.7? The 8.7. Short term, I'd want the 8.75, depends on how short term, but long term, I want the 8.7. And so therefore, the 8.7% investment is more attractive. And that's not even looking at the amount of money I have in there. But your APY is always more than, when compounding, than what you're actually paying. So any other questions? So try your problems. Tell me questions on Monday. We will spend the majority of the time in the math lab on Monday before your test.